Belief-Grounded Networks for Accelerated Robot Learning under Partial Observability, presented at the Conference on Robot Learning, November 2020. Our work introduces the Belief-Grounded Network, or BGN. The BGN adds an auxiliary belief reconstruction loss to a deep reinforcement learning agent. This encourages the agent to extract Markovian features from partial observations. Training is conducted in simulation, where the belief can be easily tracked, but the resulting policy does not require belief information and can be deployed in the real world. In this diagram, we have extended a synchronous advantage actor critic, or A2C, with our BGN. The blue components represent our additional branches added to A2C. These branches are trained by supervised learning to predict the true belief, causing gradients to backpropagate into the main network and encourage it to learn a Markovian feature representation. After training, these extra layers can be removed. We trained A2C with a recurrent BGN on 3 new force feedback robotic domains in MuJoCo, and then transferred the learned policies directly to a UR5E robot gripper with 2 degrees of freedom. Our first domain is called top plate. Here, the robot must grasp the top plate from a stack of unknown height, which is randomly sampled from 1 to 10. Motion is constrained vertically, so the agent has 3 available actions: move up, move down, or grasp. When the stack height is less than 10, the agent moves up until it no longer feels a plate. It now knows that it's above the top of the stack, so it moves back down and grasps the first plate it feels. When the stack height is exactly 10, the agent knows that there cannot be any plates above the 10th plate and immediately grasps it. This is interesting because it demonstrates that the agent has actually learned to count tactile interactions. Our second domain is called 2 bumps 1D. In this scenario, there are 2 bump objects placed on a line. The goal is to push the black bump to the right without disturbing the white bump. The relative order of these bumps remains constant. The agent can move left or right with compliant mode enabled or disabled. The agent starts at a random location on the line. In case 1, it begins to the left of both bumps. The agent begins in compliant mode as it passes over the white bump, then stiffens and continues to move to the right until it pushes the black bump. Case 2 is more complicated. The agent starts between the bumps. It moves to the right in compliant mode, passing over the black bump. It prepares to push a second bump by disabling compliant mode, but reaches the extremity of its motion without finding anything. The agent concludes that the bump it passed must be the black bump. It re-enables compliant mode, backtracks to the left side of the black bump, disables compliant mode, and then pushes the black bump. In case 3, the agent starts to the right of the black bump. The policy follows similarly to the latter half of case 2. The agent searches for a bump in compliant mode, but cannot find one. It backtracks over the first bump it feels, which must be the black bump, and pushes it to the right to complete the goal. Our third and final domain is called 2 bumps 2D. Similarly to the previous experiment, the robot must grasp the black bump without moving the white bump. This time, motion is allowed on a 2-dimensional grid. The black bump is also slightly larger than the white bump, which will let the agent differentiate between them. In case 1, the agent encounters the smaller white bump first, but it does not know if it should push it. It remains in compliant mode so as not to disturb the bump, and continues searching for the second bump. When it finds it, it can tell that the black bump is bigger based on the relative angular difference it induces on the gripper, so the agent grasps the bump immediately. In case 2, the agent encounters the bigger black bump first. It remains in compliant mode and continues searching for the second bump, like in case 1. When it finds it, it deduces that this is not the target bump, and traverses the shortest path back to the black bump to complete the goal. Our robot experiments demonstrate that the BGN significantly improves agent performance in the presence of limited observations like tactile sensation. For the full paper, check out the description below, and thanks for watching.